Introduce Shakhar Smorodinsky from Ben-Gurion University. Um, since we spent so much time adjusting the screen, I will skip the introduction for such a famous person who doesn't need any introduction. So we will let Shahar speak right now. Go ahead, Shahar.
Thanks a lot. Thank you all, the organizers, for inviting me. So I'm gonna make it sort of a half survey, talk about Zarankiewicz problem, focusing on geometry, and this is based on joint work with Chaya Keller and on a paper that appeared in SOCG 2024. And yeah, so this is part of extremal combinatorics that one could say that philosophical extremal combinatorics studies how complex can a system be while avoiding certain configurations. That's sort of the theme, and we have many examples. I won't get into the details, like Ramsey theorem, van der Waals theorem. Could be viewed as a special case of Ramsey theorem. That's about monochromatic arithmetic progression when you color the integers. Hale's duet, which could be viewed as a higher dimensional analog of van der Waals theorem, and so on. And we have also Turan's theorem. So let's dive into Turan's theorem from extremal graph theory. And this is the theorem. So let H be some fixed small graph, and one can denote the function Ex, extreme of NH, to be the maximum possible number of edges that any graph on n vertices can have if it avoids H as a subgraph. And Turan proved that if you exclude the complete graph on r plus 1 vertices, so r is some fixed integer, then this extremal function is exactly what is written here. So it's 1 minus 1 over r, roughly, times the maximum number of edges you can have. So if the complete graph on n vertices can have n choose 2, which is asymptotically n squared over 2, then if you avoid, let's say, a triangle, then you can have at most 1 minus 1 over 2, which is half of that, so n squared over 4, and so on. And avoiding here, I want to stress the fact that it's avoiding H as a subgraph, but not necessarily induced subgraph. And this is such a nice piece of information that I cannot resist stating it. Again, though I'm sure that many of you were exposed to this anecdote that Turan himself was requested to write a note of welcome to the launch of the Journal of Graph Theory in 1977. So he said that instead of writing, how nice mathematics is, or combinatoric, or graph theory, and so on, he actually wrote, I'm not going to show you all the text, but wrote about him being sent to a labor camp in Hungary during the Second World War. And there he found an escape by thinking of that problem, which became Turan's theorem, while he was actually in those camps. And here is I marked a nice sort of description where he says that while he was in this labor camp, he says, I cannot properly describe my feelings during the next few days, where he described how he got to sort of nearing the proof of the theorem. The pleasure of dealing with a quite unusual type of problem, the beauty of it, the gradual nearing of the solution, finally the complete solution, made these days really ecstatic. The feeling of some intellectual freedom and being, to a certain extent, spiritually free of oppression, only added to this ecstasy. So that is that is a nice anecdote about how he came to what happened, where he was exactly when he was thinking about the proof. Okay, so this is the extremal Turan's theorem is about the extremal function when H is the complete graph. Here is a very beautiful generalization of that theorem that says, in fact, that if you take any graph, not necessarily a complete graph, so fix H, what really matters is the chromatic number of H and not H itself. So Erdestone and Simonovich later proved this theorem which generalizes Turan's theorem because you can see here that if you plug in H to be the complete graph on R+1 vertices, then of course the chromatic number of such an H is R+1, so you exactly get back Turan's theorem. So this is a very nice sort of, you could say that it more or less closes the question of what is the extremal function looks like, but notice that when it's a bipartite graph, so namely the chromatic number is 2, we don't get the full answer here, because what we get basically is that, right, it's the extremal function of a bipartite graph is 1 minus 1 plus little o of 1 times n squared. So it only tells us that it is little o of n squared. But how little is the little o? That's the question. And that leads us to Zarankiewicz problem. So that turned out, and the first question is what happens for a complete bipartite graph? So what is the extremal function of, let's say, a complete bipartite graph, say on 2 sets of t vertices? Of course, you can ask about t and s, not necessarily the same, but let me not complicated things right now. And this turned out to be extremely hard problem until today. So we don't know much about this function, and notice that in fact, if we are only interested in the asymptotic on this function, we could in fact assume that the host graph is also bipartite. We can ask what is the maximum number of edges of a bipartite graph not containing this KTT as a subgraph, because every graph, it's an easy exercise to show that any graph on every graph contains a bipartite graph with at least half of the edges of that graph. And if the graph does not, if this subgraph, which is bipartite, that does not contain KTT, and you give some upper bound on the number of edges, then up to a factor of 2, you get the asymptotics. Okay, so the fundamental theorem that tells us sort of the most general bound is the following due to Kovaric-Shoshin-Tur, and the extremal function looks like something like n to the 2 minus 1 over t. I should have written the constant, forget the constant in the big O notation, which also depends, of course, on t. And this bound is only known to be tight for t equals 2 and 3, and the lower bound construction comes, for the case of 2, comes from there are many lower bound construction, but one of them comes from the projective plane, finite projective planes, by looking at incidences between lines and points, and for t equals 3 by lines and spheres. Okay, so this is what we know. So you see that it starts from something like when t equals 2, it's n to the 3/2, t equals 3, it's n to the 5/3, and so on. And already for t equals 4 or more, we don't know the asymptotic of this function. Of course, I'm only, just to be sort of, to make things very simple here, I only talk about KTT and not KTS, But there is a whole industry of what happens if it's T, the two sides of this little graph on bipartite graph are not, it's not balanced, and when one side is very, very big compared to the other, exponentially big, then we know that some tightness result. We have some lower bound constructions. I always maybe I'll give a very fast sketch of the proof of this theorem, because it's it's more or less a one-line proof by doing by noticing what you really need to do. It's basically a double counting proof. You count, let's say, so again, I assume that the host graph has n vertices, let's say, on each side, and it's a bipartite graph, but it does not contain KTT as a subgraph. So I will count the number of stars with apex, let's say, on the left side, and T leaves, so stars with T leaves on the right side. So of course, on one hand, I can assume that all the degrees on the left-hand side are at least T, because I will just discard all the blue vertices that have degree less than T. I discard at most NT edges. So, and still the graph that is left does not contain KTT. So I will only care about those that have a degree at least T. So of course, look at every vertex on the left-hand side. Suppose the vertex has highest degree di, then it has di choose T possible T tuples of neighbors of it that are connected to it. So the number of stars with apex at a given vertex di is di choose T. So the sum of di choose T counts the number of stars that has T leaves on the red side and an apex on the blue side. But of course, every T tuple on the right-hand side, any T tuple can be connected to at most T minus 1 apexes on the left-hand side, because otherwise you will have a KTT. So the number of such stars is bounded by T minus 1 time the maximum possible number of T tuple, which is n choose T on the right side. So this is roughly n to the power T. On the other hand, if you use convexity and you, what's called Helder's inequality, you see that, well, di choose T is roughly di to the power T times some constant. And the sum of di to the power T by Helder's inequality is at least the sum of di, all of this to the power T, over the number of summons to the T minus 1, which is n to T minus 1. And this is the sum of the degrees on the left-hand side is exactly the number of edges. So basically what we have here is the number of edges to the power T over n to the T minus 1 is bounded by n to the T. Also altogether we have this, or in other words, we have this bound. So this is the proof. And the question is, when can we get better bounds? And I will start with the case where the graph's underlying host graph has the so-called bounded VC dimension. So what is, let me give you a crash course definition on VC dimension. But before that, suppose we don't know what does it mean for a bipartite graph to have bounded VC dimension. Let me quote this nice theorem that says that if the host graph has bounded VC dimension but does not contain a KTT as a subgraph, and the VC dimension is D, then the number of edges in the graph is in fact only n to the 2 minus 1 over D. So notice that now, no matter how big T is, the exponent is fixed. It's 2 minus 1 over D. So when T is much bigger than D, this is a much better bound asymptotically, because the T appears only in the constant of the big O notation. So you have to compare it with the bound we get from Kovary-Shoshtouran, which is n to the 2 minus 1 over T. And I don't want to spend too much time, and I didn't write anything about it, but you might say, okay, I will tell you in a minute what does it mean for a graph to be so special to have this bounded VC dimension. But in fact, it's not very special because what we know is that if a graph does not contain a KTT as a subgraph, and we don't know any more properties it has, without assuming anything about its VC dimension, the VC dimension of the graph is automatically at most T plus log T. So it's not that of a cheating in some sense. So what is VC dimension? So let me, just to be on the safe side, define it. So it's a notion that you can define for general hypergraph. So we have a set of vertices, a set of hyperedges E, and we say that a subset S of vertices is shattered if you look at the pattern of intersection of S with all the hyperedges, you get the power set of S. And the VC dimension of a hypergraph is the maximum size of a shattered set. And what does it mean to, so for example, I always like to give this very simple example. Suppose our hypergraph consists of, let's say, n points or n numbers. You can think of them as n points on the line, and all the subset are all possible subset of consecutive numbers. And this is the hypergraph. So if we call the points, if we order them from 1 to n, 1 to 3 to n, so 1, 2 is the hyperedge, 1, 2, 3 is the hyperedge, 2, 3, 4, 3, 4, 5, 3, 4, 5, whatever. All the discrete intervals. So what is the VC dimension of such a hypergraph? What is the maximum size of a shattered set? The answer is it's at most 2, it cannot be 3. Because if you take 3 points, you cannot have, you cannot obtain, let's say, the first and the third one as a hyperedge when you cannot have a hyperedge intersecting the first and the third without containing the middle point. So you cannot have separate these 2 points from the third, from the middle, so you cannot shatter the 3 points. So the dimension is at most 1. You can see that actually you can get 2. And what is a VC? Okay, that's a VC dimension of a hypergraph, but what is a VC dimension of a bipartite graph? So it's very simple. We just look at the bipartite graph as a hypergraph where, let's say, for example, you can look at the left-hand side as the vertices of the hypergraph, and the right-hand side, you look at every vertex. On the B side, you look at the neighbors of that vertex, and that's a subset of A. And this collection of subsets, collection of neighborhoods, is your hyperedges. And the VC dimension of is that the dimension of that hypergraph. Plus we add that yeah. Well, we can think of all the vertices of the graph as vertices of the hypergraph as well, and all the neighborhoods as for generally all the neighborhoods as the subsets. And so in other words, VC dimension is the maximum set of vertices such that for every subset of that vertices there is some vertex that is connected only to that subset among them. Okay, that's the VC dimension of the hypergraph. For example, here is a subset because there is a vertex here that is. Can you see the mouse that I'm? Yes. Okay. It will be nice if I see some of you. I don't know how many with the camera, but it's very intimate. Okay. Okay. I don't hear anybody. I hope you can hear me. So recall that this is the theorem that Fox et al. Proved that for this case, when the hosting graph is bipartite and has VC dimension D, we have this upper bound. In the exponent, we have 2 minus 1 over D, even though he could be much larger than D. And when the host graph is balanced, namely it's a bipartite graph with the same number of vertices on each side, then in fact there is an improvement that shows that for VC dimension D, the real value of this extreme function, KTT graph, is it should be O little o sub t. So it's little o of n to the 2 minus 1 over d. This is this special case. Okay. So where else can we do better? Well, we have the natural instance of such graphs in incidence geometry. For example, the classical setting of lines, real lines in the plane and points. You can define a bipartite graph. The points are one side of the graph, the lines are the other side of the graph, and a point and a line are connected if the point is incident with the line, namely the line passes through the point or the point lies on the line. That graph inherently does not have a K22 as a subgraph, because you cannot have 2 points and 2 distinct lines simultaneously passing through these 2 points. That cannot be. So you cannot have a K22 as a subgraph. So Kovary-Shosh-Turan tells us that the number of such incidences, or the number of point lines that the line passes through the point, is at most n to the 3/2. That follows from. However, it was a celebrated result of Smorodinsky that in fact proved that the number of edges in such a graph is at most n to the 4/3, and this was known to be tied by a simple construction on the grid, I think due to Erdős, who in fact maybe asked the question about how many point line incidences can you have. Okay, but this is sort of a setting where we look only at the host graphs that come from incidence between points and lines, and they already have the feature that they do not contain K22 as a subgraph. Another famous problem is the unit distance problem, which asks that among n points in the plane, how many pairs are at distance 1? So that's basically a question on a graph. You look at a family of graphs that can be realized by taking the vertices to be some points in the plane, and the edges are those pairs that have a Euclidean distance exactly 1 between them. And the number of edges is the number of such pairs, and you can so see I formalized the U of n to be the maximum possible number of pairs at distance 1 among n points over all possible sets of n points in the plane. This is the famous Erdős repeated distance or unit distance. And this is a big open problem. No, there's a big gap between what is known about the upper and lower bounds. And I urge you to improve it and to earn $500 from Erdős. By the way, the current best bound, so the lower bound is already it hasn't been improved for almost 70 years, or maybe it is yes. So it's slightly more than linear, and the upper bound was first proved to be n to the 4/3 by Spencer Smorodinsky, and it was and there are many nice proof of several proofs of that. They were the first to prove that. So what does this have to do with Zarankiewicz? Well, first of all, notice that again we have inherently in the problem that such graphs do not contain K23 as a subgraph. So unit distance graph cannot have a K23 as a subgraph because suppose you have 3 points and 3, let's call them the red points, and 1 point that is connected to all the 3, meaning that it's the center of a unit circle that passes through the 3 points. But 3 points can have at most 1 circle passing through them, so there cannot be another point at the same distance from all these red points, even if the distance is any distance. So you cannot have 2 blue points that have the same distance to given 3 points. Okay, this is one way to look at it. Okay, so again, if this point is a distance 1 from this tree, then in particular, it defines a circle, a unique circle passing through the 3 points. And what does this have to do with incidence geometry? This is another way to look at it. Well, it's in fact equivalent to the following problem. I just got a warning that I have a Zoom seminar because it wasn't aware that actually the time in Israel have moved 1 hour. Okay. So fix a set of points that, and you suppose you want to bound the number of pairs at distance 1. And what you do, so you look at these endpoints and you look at the set, another set of unit circles centered at the points of P. So let's say we have 4 points, we will draw 4 unit circles. For each point, we'll draw a circle centered at this point. And now notice that the number of incidences between the circles and the points, so the number of pair circle points such as circle passes through the points, is exactly twice the number of unit distances, because every time we have a pair at distance 1, it contributes, if you have a pair of distance 1, there is a circle centered at the first point that passes through the other point and vice versa. So you get 2 incidences, exactly. And you can see that it's the other way around. If you can bound also the number of incidences between point and unit circles, you will get asymptotically the answer to the unit distance problem and vice versa. And if you get so these 2 problems are equivalent, and they are very hard. There is a big gap between the upper and lower bounds. Here is a more general setting that rises in let's say in incidence geometry. But before that, let me say that I gave the 2 examples I gave until now have the property that the hosting graph inherently does not contain some biclic. But it could be, for example, that you look at a geometric setting. For example, you look at, let's say, n planes in 3D, 2-dimensional planes in 3D, and n points in 3D. And you want to bound the maximum number of incidences between planes and points. So without assuming anything further, this is a trivial question, because if you just put n points on a line, n distinct points that are collinear, and n planes, all distinct planes, all passing, so a pencil of planes passing through that line, then every plane is incident to all the points. So we have n points and n planes and n square possible incidences. So you must assume now that to get some interesting result, at least that you don't have some small biclic. So this is a natural question. Can you do better than Kovary-Shosh-Turan? And here comes a beautiful, very general theorem by Jacob, Janusz, Adam, Andrew, and Joshua that says the following. Let me demonstrate. It's a much more general theorem in various dimensions, but let me demonstrate first in the plane. Suppose we have two sets of endpoints in the plane, and we define a graph that is defined, let's say, by some polynomial. So it means that you take 4 variate polynomials. You take 2 points and you plug them, the coordinates, so you have altogether 4 coordinates. You plug them into this polynomial. The polynomial is a 4 variate polynomial. And if this fixed polynomial, let's say, is greater than 0, you put an edge in between these 2 points. Okay? And suppose this graph also is KTT free. So we must assume that, because what I gave you as an example is a particular example of such. So we call such graph semi-algebraic. And more generally, you can think of let's say, 2 sets of points in RD. So each pair of points, you can think of it as 2D numbers, which you plug into a 2D variate polynomial. And if this polynomial is greater than 0, then you put an edge. Now we don't need the restriction that you have only one polynomial. You can have a zillion polynomials as long as they are constant, and each polynomial will have a different restriction. So one has to be greater than 0, the other has to be 0, or less than 0, so on. So there's some fixed Boolean combination of some fixed number of polynomials of some fixed constant degree. And whenever you have 2 points, you can see if this Boolean formula is satisfied. If so, you put an edge in the graph. And if the graph does not have and that is called a semi-algebraic graph. If the graph is KTT free, what they prove is the following theorem, that in the plane, we have this upper bound n to the 4/3 no matter what T and R are. R is the complexity, so the degree and the number of polynomials and so on. So basically, it is an extension or far-reaching generalization of semi-ready-Trotter, because semi-ready-Trotter, a point passing through a line, we can define using one polynomial. And so you have to compare it to 2 minus 1 over t. So n to the 4/3 is the best you can have, because we know it's also a lower bound by the lower bound construction of semi-ready-Trotter. In higher dimension, we get something like n to the, so if you have two sets of n points in RD and a semi-algebraic graph defined on them, and that graph does not have a KTT, then again, look, the bound is free of t. It's only the only parameter that is interesting is the dimension of the point set. So it's 2 minus 2 over d plus 1, and even there you have to compare it. Well, I skipped many details, but those graphs usually have bounded VC dimensions. So you could have used the fact that bounded VC dimension gives you something. But look, we have the bound for bounded VC. Let's say if the VC dimension is D, then we have 2 minus 1 over D. But here we have 2 minus 2 over D plus 1. But it's much better than for most D if you replace 2 over D plus 1 with 1 over D, you get a worse bound, which you could get from VC. Okay. So this is the result of our semi-algebraic graphs. And can we do even better than that? So again, most of the things you get in incident geometry are basically semi-algebraic relations. But sometimes you can do much better than this bound. For example, look at the problem of bounding the number of incidences between points and axis parallel rectangles in the plane. So here is a result. So if you have n points, this is one side of the graph, and the second side of the graph is a set of n axis parallel boxes in RD. And you look at the incidence graph, namely, you put an edge between a point and a box if the point is inside the box. Of course, you need to assume that the graph does not have a KTT. But now we get a bound which is near linear. Look, it's n times polylog n. This is what Basit et al. Proved not so long ago. And in fact, it's not far from the truth. Already in the plane, one can show a lower bound of n polylog, n log over log log n. And there was a slight improvement when d equals 2 to n log n for the upper bound. Okay. So this quasi-linear upper bound motivated Chen and Arpeled to study many other cases where it's a KTT-free incidence graph of points and some n geometric objects. So I give you just a sub list of what they did. So they showed that if you have such an incidence graph between points and geometric object, and it is KTT free. So the number of edges is bounded by what you see in the second column, and I gave you only an example. So they improved, first of all, the bound of Basit et al. From log n to the power something to log n over log n, and they also gave an almost linear bound for what is called pseudo disk endpoints in the plane, or disks endpoints. They gave a linear bound and half-place endpoints and so on. So here from now on, I want to show you some sort of another way to attack Zarankiewicz problem, but from a different angle, and I'm going to be slightly more technical, and I want to focus on this part just as a sort of showcase. So I want to show you how to prove a linear bound. So that's improving to a linear bound, but using it, actually extending it not only to pseudodisk versus points, but pseudodisk versus pseudodisk. So now we will talk about intersection graph of pseudodisk and pseudodisk. So you can think of incidence graph of points and disks as an intersection graph between points and disks. Because if the point is inside the disk, there is a non-empty intersection between the point and the disk. So now you can talk about disks and disks. But not only disks and disks, but pseudodisks and pseudodisks, where a pseudodisk family is a family of simple closed Jordan regions, such that the boundary of every two intersects at most twice. So if you don't know what pseudodisk, or it confuses you, just think of the problem as an intersection graph of two families of disks. So we ignore in the graph, we ignore the interfamily, so the intersection inside the family. So we don't count blue-blue intersection, we don't count red-red intersection, we only count blue-red intersection. So it's a bipartite graph. Okay, so what we are able to prove is that if such a graph is KTT free, then the number of edges is linear in n, where the constant, only the constant in the big O notation depends on t. And in fact, it holds also for something that is called non-piercing region. So this generalizes the notion of pseudodisks. Non-piercing regions, so a family of regions is said to be non-piercing if for every two members, if you look, let's say, alpha and beta, alpha minus beta is connected and beta minus alpha is also connected. So okay, so for that, to show you how we tackle this problem of Zarankiewicz, I want to introduce the notion of epsilon t-nets. But for that, I also have to mention what are epsilon nets for hypergraphs. So epsilon nets are simply heating sets in hypergraphs, but only for the large hyperedges. Large meaning those hyperedges that contain at least epsilon fraction of the vertices. So a subset is a heating set if it has a subset of the vertices is a heating set for the hypergraph if it has a non-empty intersection with every hyperedge. So for example, here is the subset of the red vertices is a heating set for this hypergraph. And an epsilon net is a heating set only for those hyperedges that contains at least epsilon times this V vertices. This is an epsilon net. And this, this reminds me that in this conference in Athens, just before I gave the talk, Jack Snoink told me that he just saw this car outside the conference venue in Athens. So as you can see, it says epsilon net on the car. Okay, so let us generalize this notion of epsilon net. So suppose now we we want to find a set not of vertices, but let's say t is some integer. Think of it as 2. So we want to find a set of t-tuples. And what we want is that every hyperedge, which is heavy, namely still contains epsilon fraction of the vertices, will fully contain one of the t-tuple. It's not enough to intersect a t-tuple, it has to contain a t-tuple. For example, for t equal 3, we see a bunch, like 3 tuples of 3 vertices, such that all the big hyperedges fully contain one of these tuples. So are there any questions? Is everybody still alive even? Okay. So what is the idea? So first of all, so let's look at this bipartite graph where on parts A and B, where A and B are 2 families of disks. It's actually pseudo disks, and each of them, let's say, have cardinality n. And the edges are those pairs red disk and blue disk that have a non-empty intersection. What we need is the following theorems that says that this neighborhood hypergraph, so let's say you look at all the pseudo disk in A, and you look at all the subsets of A that can be realized as intersection with some guy in B. So every guy in B, if you look at the set of the A guys that it intersect, that's a subset of A. So we define a hypergraph here, and that hypergraph admits an epsilon t net, so a collection of t tuples basically, and the collection has size only 1 over epsilon roughly, with some hidden dependence on t. Which means basically that for any epsilon, one can take a collection of t-tuples. The number of t-tuples is only 1 over epsilon. It's a t-tuples of disks. And the number of t-tuples is only 1 over epsilon. And we have the property that if a disk in B intersects at least epsilon n disks from A, then one of the t-tuple, it will intersect completely one of the t-tuples of disks in A that we took. That's basically what it means. In the terms of in graph theoretical terms, it means that we can find. Okay, so is it clear what is the theorem? So we prove that one can have for any t constant an epsilon t net for this neighborhood hypergraph. It goes in both ways. It goes also when B are the vertices and A defines the hyperedges. So we have this epsilon t net, which is very small. It only have size only 1 over epsilon. And now, so we need to understand what we have, what tool we have to, and we're almost completely done showing basically the approach how to bound the number of edges of such a graph. So recall that now we have A is a bunch of pseudo disks, B is a bunch of disks, and a blue and red are connected if they have a non-empty intersection. So what we will do is the following. We will just first distinguish between high degree vertices and small degree vertices. So we call them light vertices and heavy vertices. Light vertices are those that have degree at most epsilon n, and high degree are those that have more than epsilon n, and so on. Now, the light vertices, we don't care about. I mean, if a vertex has degree at most epsilon n, maybe there are n such vertices on one side, maybe all the vertices are like that. They can contribute at most, each of them can contribute at most epsilon n edges. So there are n such, there might be epsilon n square such edges. So the question is, how many heavy vertices can we have? So the claim is that the number of heavy vertices on each side can be at most 1 over epsilon. And why is that? because what we will do, we will take for A the epsilon P net. So recall we have 1 over epsilon T tuples in A. So T tuples of vertices from A. And we know that every heavy vertex in B must be a neighbor of some T tuple. Okay? But such a T tuple, a fixed T tuple, can be a neighbor, completely a neighbor of at most T minus 1 such vertices. Because if there will be T vertices that are all connected to all these T tuples, we will have a KTT in the graph. So every T tuple can be connected to only one T minus 1 such heavy vertices that contain this T minus 1, this specific T tuple. But we have at most 1 over epsilon roughly T tuples. So altogether, how many heavy vertices we have on the red side? At most 1 over epsilon times T minus 1, or order of 1 over epsilon. So this is the number of heavy vertices on the right side, and the same goes for the left hand side. This is where we use the epsilon T net. So once we have this, the analysis is very simple, because we will choose in fact epsilon to be very small. It will be a constant over n, some constant depending on T over n, and we will do the following. So every edge that has an endpoint of in a light vertex, which could be light heavy, heavy light, light light, no, all kinds of edges. All these edges can be accounted. There are at most 2 times epsilon n times n such edges, which is roughly epsilon n squared. And we will basically and now we will look. So we count all the edges that have a light vertex incident to it, like one side. The rest of the edges are the heavy edges. So that is basically an induced. So if you take the heavy vertex on one side and the heavy vertex on one side and look at the induced graph on that vertex set, this is still the same. It has the same property that we need. So you can use induction. It's basically you can basically write a recursion formula here. You can say the number of heavy vertices is order of 1 over epsilon. So the total number of edges is at most the number of edges that come from some light vertices plus the same number on 1 over epsilon. If epsilon is roughly T over n, the first term becomes linear, and the second term becomes, you can make it to be, let's say, n over 2. You can choose the right parameters, so you basically get this formula. And this solves to linear. So basically, the number of edges is only linear. I think I will stop here.
Thank you very much.
Very interesting. Thank you.
Oh, I should have said that maybe that, so what we see here is a sample, let's say this case, so we see history of 2 settings. One is an incidence graph of point versus pseudodisk, or the more general, the intersection graph of the bipartite intersection of 2 families of pseudodisks. So if you just plug in Kovary-Shoshtern, you get those bounds. If you look at the VC dimension argument, so again, what's nice about pseudodisk is that it is not, you cannot define it using a the setting of semi-algebraic graph, because the curves bounding pseudodisk could be not even algebraic. So the realm of semi-algebraic graph does not hold, but the VC dimension does hold. So what you see here is using the fact that the VC dimension of the underlying graph is bounded. Then Chen and Appellate did something using other methods, such as biclick cover, shallow cutting lemma, or whatever. and they improved it. And here we saw a very simple approach that gives a tight linear, almost tight linear bound. So that's all. That's all, folks.
Thanks again. Questions, suggestions, comments, improvements?
I wonder something. It's probably not that relevant, but I'll ask anyway. Your problems remind me of a big problem. So as you know, the distinct distances problem is reduced to counting intersecting lines in 3 dimensions. And there's a bipartite version of this that's still wide open. What happens if you have red lines and blue lines in 3 dimensions and there are all sorts of restrictions on them? How many pairs can intersect? And actually, the unit distances problem can be reduced to such a problem also. Do you think there's any relevance of such approaches there?
So you remind me that in sausage, Xavier asked me some similar question about intersection graph of red lines and blue lines not having something, but he gave the restriction in terms of some algebraic restriction on the two set, but he said that it follows that this graph does not have a KT3 as a subgraph. So what is the restriction? Does it? I mean, it's very important if it's K33, K22, what exactly we don't have there. If it's a
Right.
K22 or K33, then we might look at this epsilon 2-net approach, see if we can get something, right? That's basically
Uh,
the thing that.
so you have there all sorts of there are all sorts of restrictions there, like not too many lines in the plane, not too many lines through a point, stuff like that. I forget what it means in the terms of the graph.
Yeah, so
Okay.
not too many lines in a plane, not too many lines on right.
There's more,
Really
but
remind me,
no,
I
okay. I mean,
actually
I can look at it again
I
if you want.
actually
I
wrote
didn't.
it. So I actually, you know what? I maybe even have it written here somewhere that he told me exactly what is the. So it seems that it's really the same question.
It's probably yeah, that's the unit distances basically. It's probably the same.
But no, but it was he didn't mention unit distance. He didn't mention any of. He just mentioned the setting of. It's really written here. Let me see. So I even have the what we got. I think we got it in. No, we got it in. So didn't we get it there? Oh no, it's yeah, we get it. Or maybe I already, I think my daughter maybe ripped off the relevant part. And I don't, maybe I do have it. Ah. I think that, yeah. Oh, no, it's not the right, yeah, I don't have it.
Okay, never mind. If you ever want, I'm happy to show you what I'm talking
Yeah,
about in more
so
detail.
I remember that, yeah, it's very interesting to see. So basically, the interesting part is to see where can you get a linear, almost linear epsilon t net.
Oh, so
Or
yeah,
let's
I
say
mean
say
that
that
would
it's
give
small,
an almost
not,
linear for distinct for unit distances. That's
what?
ambitious. If you get almost linear, you get almost linear bound for distinct for unit
No, no, no,
distances.
no.
That's
No, there are two things. One, to get the size, well, we have a theorem that says that for any graph, hypergraph bounded VC dimension, the epsilon t net always, there is always an epsilon t net of size 1 over epsilon log 1 over epsilon. The
oh
same
okay.
like when. So that is good. The problem is that we cannot start with epsilon being 1 over n, a constant over n. We have to start with a much bigger epsilon. But maybe in some cases, like we have in pseudodis, we can start with an epsilon that is small enough to let us. So notice that in the last slide, I said that I will choose epsilon to be some constant depending on t over n.
Yeah.
So that was a very special to what we can do with pseudodis.
Okay. Well, I'm curious. I'm
Yeah,
think I'm look more carefully at
we
your
can talk
paper.
about it. We can take it.
Also, sorry if taking over the conversation. A few months ago, there was an interesting paper by Barry Sudakov and some of his people.
Yes. Yes.
Is that okay? Okay, so
No,
you know my
that
question.
about so related to bounded VC dimension, you mean? This
So
is
they basically they look at planes in 3 dimensions, incidences with planes in 3 dimensions, and basically they show there's one forbidden configuration. You can have a K33, but you cannot have something weirder.
yes.
That's
So
basically
they have there is a parallel industry going on to geometry, which is now being coined as what do you call it? Degree boundedness. But more generally, what I wanted to mention it, but I thought I will not have time. So in the setting of the extremal function, so graph does not contain a KTT. Assume that so I mentioned bounded VC dimension. So not only that the graph does not have a KTT, but it has bounded VC dimension. So instead of bounded VC dimension, they're interested in not containing a KTT as a graph,